co-founders and CEO here at Snorkel. I'm also on faculty at the University of Washington in the computer science department. And I'm really excited to and privileged to get to speak with Mayee today. So Mayee, if you don't mind introducing yourself, and then we'll jump in.
Okay. Hi, everyone. My name is Mayee Chen. I'm a PhD student in the computer science department at Stanford, advised by Chris Ray, working on some broad themes of understanding data-centric AI, weak supervision, and theoretical machine learning.
I'm so excited to speak with you today. Actually, even before we started recording, I already revealed a whole different direction that of your work that I'm super excited to find out the latest progress on. But today, we'll focus on since we just have a few minutes, on the LIGER paper. So I think that the title is Shoring Up the Foundations, Fusing Model Embeddings and Weak Supervision. This is an awesome paper of one of these kind of intersectional studies of how do you take, two major ideas around, in some ways, how you can be more data efficient, how you can actually accelerate data-centric AI, and put them together in a really smart and principled way that actually has impact. But I'll let you actually intro it. So I guess, and this was I think a UAI paper, if I'm not mistaken.
Yes, that's correct.
Yeah, so maybe you could tell us a little bit about the paper and the work.
Yeah, sure. So I think the motivation here is that foundation models are like a very new and exciting paradigm. These large pre-trained models such as GPT-3 and BERT and CLIP and DALL-E. And they're very exciting because they can allow you to construct models like out of the box with very limited labeled data or labeled examples. But the challenge there is that it's not really clear how to apply these foundation models when we don't have any labeled data at all. And so here we draw upon a lot of excellent recent work done in weak supervision, which is a nice programmatic way of producing labeled data from unlabeled data in these weak sources that can be things like heuristics, crowd workers, external knowledge bases. So we're interested in looking at the intersection of these two concepts, foundation models and weak supervision. And the nice thing here is, if you think about it, they do offer like complementary sources of signal. So foundation models, they're pre-trained on huge corpuses of data that's like massive, and they have a lot of general information from the web or from these data sets. And on the other hand, weak supervision, these practitioners are writing or specifying these sorts of functions. And so these can have very tailored, high precision, but low coverage sorts of signal. So it feels we can combine them and get the best of both worlds. And that's what this paper looks at. And I can go into more detail, or I don't know if you have any more questions there.
Yeah, first of all, I think it's an awesome idea. I'm just echoing what you said. It's these kind of complementary ideas of, just taking a step back. One idea that I think many of us have thought about with this kind of programmatic supervision or weak supervision work or one way to view it is this idea of trying to bridge expert knowledge with kind of statistical or data-driven knowledge, right? You have something that a domain expert can say that's very targeted and specialized at the task you're trying to accomplish. Probably the foundation model is not that kind of specialized or fine-tuned for that task, just when you look at real world things. But this expert knowledge, especially if you try to write it down as a program or a heuristic, or we call it a labeling function, often is going to be very brittle. Whereas you have these foundation models that are extremely good at generalizing, but they're very general, right? They're not targeted at the specific task. So using the one to complement the other or bridging between them, that's one way that I had thought about your work and some of the bigger objectives here. So maybe one way to take this would be, what's an example of where you might want to use this kind of approach where you're mixing programmatic supervision with foundation models?
Yes, that's a great question. So what you just said, I really agree with, is we need additional information to often adapt foundation models to particular tasks. And so in our setting, actually, rather than looking at like the full foundation model itself, which is like very difficult can be expensive to fully fine tune, we're just saying, suppose we only have access to the foundation model's embeddings, and you can usually get those via some API for all these big models. And so our approach is essentially, the ingredients we have are foundation models, embedding space, to think about it a bit more theoretically. And then we have all these labeling functions of these weak sources of signal on our unlabeled data that are offering a vote on each data point for what it should be. And our framework is very helpful in these settings where traditional weak supervision tends to actually fail a bit. And so our approach to this problem of combining foundation model embeddings and weak supervision was to say, what are these main challenges of main modeling challenges in weak supervision, and can we use like this nice embedding space to solve them? And so I'll briefly go over the two challenges. So the first one is that weak supervision typically models like the accuracy parameters for each weak source at a very coarse level. So what this means is that for each weak source the user specifies, we give it a score that's just like a complete scalar. And we wait, when we're combining this source's vote with other sources, we're just going to give it that scalar weight, regardless of what sort of data point you're seeing. And so this isn't going to really capture variations in your data set. So if you think your data set actually consists of two categories or two subgroups that have very different label distributions, then learning an accuracy parameter on your entire data set and not the subgroups is going to be a little bit imprecise potentially. Tackle that by learning these clusters in the foundation model's embedding space and providing those clusters as the subgroups and basically learning a weak supervision model on each of those clusters. And then the second challenge I'll quickly go over is that the weak sources tend to abstain a lot. So users will write very precise labeling functions, but they tend to only vote on very small sets of your unlabeled data. And oftentimes the labeling functions will actually just abstain instead. And this abstain rate can be really high. And basically, if you have a point where all of the sources you've specified abstain, then you're in deep trouble, basically. So we propose to do this sort of k-nearest neighbors type of extension per source in the embedding space. So we're essentially propagating the votes to nearby points that have abstains. For instance, if we have a labeling function for sentiment that like fires on the words like awful or terrible, then it's not going to catch the word horrible. But we know that horrible is like essentially very similar to terrible. These words are going to be embedded very close together. And so our method will capture these like extra keywords that might have slipped by, or these like similar concepts that might have slipped by when the user was writing these labeling functions.
That makes a ton of sense. If I could try to read it, I know we're almost out of time, but if I could try to read it back to you quickly. Imagine you're trying to, take a canonical ML problem, the spam versus ham problem. Is this email spam or not? And of course, this is not necessarily the hardest problem, and there's lots of labeled data. And just as a quick example, if you have a really challenging version of this problem and you want to, let's say, apply a normal model, a foundation model, the classical way, you have to just label a bunch of data by hand. Now, the first jump that puts us in this kind of weak supervision or programmatic supervision world is, let's try to write functions, or let's try to programmatically supervise. So let's ask our email spam expert to say, what patterns should we be looking for? What labeling functions? And now this email spam expert comes and says, okay, I'm looking for wire transfer. If I see wire transfer in the email, I think it's more likely to be spam. And then we kind of have these two challenges. Where is that a good labeling function? Where is it a bad one? Maybe we want to learn that it's actually a really good indicator of spam in general email, but in emails from certain, it's actually quite the opposite. It's actually quite inaccurate as a signal of spam. Second of all, we also want to handle more generality of the patterns. Like maybe it's not just wire transfer, it's money order, cash. There ends my knowledge of the financial transfer system. Yeah. But is that a fair capture? It's how do we know, we take in these programmatic supervision inputs, how do we know where to trust them versus not at a more granular level? And how do we generalize beyond the brittle pattern by which, or within which they're expressed originally? And you've been able to solve that using these embeddings from foundation models with principled kind of underpinnings in this work. Is that a fair readback?
Yeah, that's completely correct. Your example is really good. I was trying to think of one while talking, but that was really good. Yeah, so that's basically what we do. And the nice thing about the principled aspect of it quickly is that we have like theoretical guarantees for our entire framework. And of course, they're in the paper. But the key thing they rely on is this notion of the embedding space's smoothness with respect to the task you're evaluating on. So we have this quantity we can measure that kind of corresponds to how well aligned your foundation model's embedding space is with the task you're looking at. And we actually took a metric and we looked at it for different sorts of embeddings. So for some vision tasks, we looked at clip embeddings versus raw pixel space, and we confirm clip embeddings give us like the best version of our framework, and they are also the smoothest with respect to the tasks we evaluate on. So it's a very cool theoretical connection there.
Yeah, that was super cool also. Usually the only mapping you have in a lot of these bounds is sample complexity or number of data points. And here you actually have this kind of curvature or embedding space parameter that you can actually map to real world data sets. Super cool to have that tighter mapping to the theoretical bounds. Maybe that's a perfect plug, especially for theory nerds that are watching this video, but really for anyone interested in these kind of practical applications of data-centric AI and programmatic labeling meets foundation model. I can give a quick plug. Foundation Model Summit. It's going to be on January 17th. A lot of data-centric programmatic supervision meets foundation model stuff. And most importantly, Mayee, thank you so much for taking the time today to talk about your awesome work.
Yep. Thank you so much for having me.